As extreme weather events become more frequent and severe, we are faced with an urgent question. How do we predict the unpredictable? That's something that governments, scientists, and even homeowners have to grapple with. I'm Tasmin Lockwood, a reporter at Digital Frontier. Join me as I explore how AI is revolutionizing climate risk.
I'm a professor of hydrology at the University of Reading. I work very closely with weather forecasting centres and flood forecasting centres around the world. We've got lots of things changing at the same time on our planet. We're doing all number of things to it. We've also got heavy rainfall. We know that there's going to be influences on sequences of storms and the jet stream and the position of the jet stream and what that means for our weather in winter. The human behaviour, the changes to the landscape and how much rain it can soak up, but also the changes to our rainfall characteristics.
Yeah.
Of course, you've also got temperature changes, relationships between drought and floods are quite strong. And that's just one place on the planet. We're only standing here in Reading on the Thames, and we think about what's happening with monsoons, tropical cyclones and hurricanes and the changes to the rainfall there. There's a lot of change in risk across the planet that we need to understand. My research is looking at how water moves, from rain all the way over the land, through the soil, how it ends up in the river, and how we can predict that ahead of time so we can make useful decisions to get people out of the way of floods. I do a lot of things kind of on the global scale, so with big environmental models, big weather forecasting models, and following those little water droplets all the way across the world, really, which is quite a difficult job. But I also work with communities as well. Down at the end of the chain, that's really what we care about, isn't it? That people are prepared for floods and they know what to do when a flood is coming. Around the world, really interestingly, a lot of our river flow measurements come from people looking at a stick still. It is, a measurement stick sometimes it's planted in place on the riverbank because the world is a big place and it costs a lot of money to measure river flow. There are much more exciting technologies being developed using drones, so using thermal imagery as well. That's quite an exciting new technology, so we can actually see the swirling of the different water temperatures as well. So we use computer models to do lots of different things. But when we're thinking about floods, we can do ahead of time, we can say tomorrow is a flood going to come and hit my house? A week from now, is a flood going to come? And then we can prepare for that. And that's the forecasting period where we can use our models to say what's going to happen hours, days ahead, maybe a few weeks ahead. We can use those models to say, 100 years from now, what's the flood risk going to be like? Or maybe 2 years from now, what's the flood risk going to be like? So where is it safe to build? Where should we put our roads and our electricity infrastructure and things like that?
Some young companies are using advances in technology to do just that, to help insurers and society as a whole better understand their risks to the effects of the climate crisis. I sat down with ClimateX, which is one such company. Co-founder Camille Cluse explained how the company positions itself as the Google Maps for climate data.
Global GDP is expected to reduce by up to 25% by 2050 at the back of the climate change. So if you imagine 1 in every 5 pounds in your pocket disappearing at the back of something that you can't quite control, this is pretty serious. We literally had a few years ago first wildfires in the UK, imagine. And they have been spontaneous, like they didn't actually, they weren't caused by human interaction. With that, what I think started to happen as well, the businesses started to understand that the assets and that you currently have might be overvalued. ClimateX, we look at kind of all of them. You can look at the different classifications, but what we cover is between 60 to 200 asset types. But I think now that globally this problem gets more attention, there's obviously more money invested into it, and the better results of the actual model and the capture of it. So imagine building anything to do with climate. You need to sort of create like a digital twin of the earth. So you want to recreate everything from what's under the ground. So you want the rocks and you want the soil because that impacts things like subsidence and landslides. You want all the stuff on the ground, which is, your vegetation, your roads, your assets. You need to look at the rivers, the bodies of water and so on. And you want to capture this all because they will have an impact on the final outputs of the models. And finally, you want to capture what's on the air. So, all the wind, all the temperature, all the rain and so on. So to capture this stuff globally, that requires humongous amounts of compute. The servers we are using, they're already net zero. Now, when it comes to the Gen AI, yes, it does take a lot of energy to train these models. However, whatever we use and take care of, we actually do carbon removal, so we pay for carbon removal services. I don't believe in carbon offsets, therefore we actually paying for carbon removal.
Yeah.
And this is the right way to do it. So we do take those things into consideration.
Can you give us an example of like an at-risk area or building? You know, we're sat here in central London. So tell me if there's anything we should be concerned about.
There are a few different hazards that can happen to UK. I think flooding is obviously fairly obvious. Every 2 to 3 years, we get major flooding of King's Cross Station. Now, this type of event will be 3 to 5x more likely by 2050. And there's not really much that we can do to prepare against that, except from putting better drainage, or you can do some individual asset adaptation or protection themselves.
Do you have an example of a like real world impact as well, where you've been able to give this information to someone and then they've been able to go away and make the appropriate adjustments or adaptation measures?
Yes, we do work with most of the commercial real estate and asset managers, and effectively we help them. When we provide our data, we don't just stop at providing this is bad, this is the risk, this is what's going to happen, but we also help them work out the ROI on what kind of capex expenditure, so what kind of investment they would have to make to improve these assets so that it's resilient going forward. Do I need to pay a little bit more, or do I need to sell it at a loss? Or can I just divest my portfolio elsewhere? So we do help them make those decisions.
So this use of technology, software, artificial intelligence, it all is basically feeding into real world actions that need to be taken.
That's correct, yeah.
Because it's quite interesting, like a lot of people are hailing AI as the solution to everything, right? But is that realistic?
One of the key challenges right now that science faces, it's scalability and accuracy of these models. So we do believe that with the very, very major improvements that we've already seen in terms of how AI can replicate physics, with some of the examples of Jenkins modeling where they already started replacing the physics-based weather forecasting with AI, we do believe this will then propagate to climate. Also, if you think about modeling climate, UK Met Office probably needs 2 supercomputers, 2 or 3 years, and some 200 scientists to actually do climate modeling that has a really decent resolution of sort of 2 to 8 kilometers in the UK, right? This is the amount of expenditure investment. Now AI can shorten this and also get it more accurate, but we also need time to develop it.
You can't just concentrate on the technology. We could have the most sophisticated computers running the most sophisticated flood forecasts in the world, which we do, but they'd be not any use at all unless the people who are receiving them knew what to do with them. These are the things that are most important in that whole chain. The technology is really important, to get good flood forecasts out there, but it's equally important that the community knows what to do, the community has the resources that it needs to take those decisions carefully.
You mentioned sort of the insurance industry just right at the start. A lot of companies that I speak to doing sort of the intersection of AI and climate risk is targeted towards that industry, so they have a better understanding of their exposure to potential threats in the future. How do we begin to democratize this type of information when we're talking like more in the long term?
Yeah, that's a very interesting question, and it's always a tension between the insurance industry and communities who want that information. A lot of that information is proprietary, and they don't share it unless there's some very specific circumstances. I think what we have seen there is a move towards open modelling, open data in lots of places. So I work very closely with the European Centre for Medium Range Weather Forecasts here in Reading, and they have an open data policy. So their weather forecasts, and the flood forecasts that we produce in the European Flood Awareness System and the Global Flood Awareness System are all open.
Insurers may be forced to be more collaborative as they are being challenged by big tech, which is making some of this data publicly available. Back at Climate X, I sat down with senior data scientist Jamie Taylor to figure out how the company is using publicly available information and applying it to AI to come up with their risk models.
And my role is basically completely using machine learning and AI to kind of automate human processes.
What other applications of machine learning and AI are you excited about within what Climate X does, and then maybe more broadly as well?
So we've kind of used a lot of buildings data. So we have, like, when we want to tell you how much climate risk is actually going to impact your building, like knowing how old the building is, knowing what it's made out of, how tall it is really going to transform like how much damage a flood will do compared to like a big building versus a bungalow. That data is not always there, but you can find like small patches of it. So you can train machine learning algorithms to like predict those kind of building characteristics for you. So you have like, if you're predicting on like one building, say this one, you grab a set of features and they might be like, you from the satellite imagery can maybe tell how big the building is. You can also tell like what kind of roof type it has. So like you could tell if it was like a thatched or like brick or like I guess you have like grass, but like etc. Like those kind of things.
Yeah.
So you can tell also like the shape and like the orientation. So those kind of things, you can also tell actually as well, like how many buildings are around it, which is quite a good, like, especially in cities, like newer buildings are usually in cities and there's a lot of buildings around it.
And that all impacts the climate risk.
Yeah, so like the age of the building, and then like we combine at Climate X, we'll combine our physical risk models. So that's when we talk about floods, like wildfires, etc. One of our selling points is that we don't just tell you, like, oh, there's going to be a flood here. We tell it like what it's going to do to your building. And that's combining like the physical models, then with the machine learning models. Like
AI is both a contributor and a solution to the climate crisis. So just how important is AI in understanding climate risk?
I work with the European Centre for Medium Range Weather Forecasts, UCMWF, and they have now an AI weather forecast that is operational. That means it's running every day, 24/7. It's being fed out to everybody who can use it. So the fact that that is now up and running, and it's taken maybe only 2 years to get to that point. The development rate in AI and machine learning is just incredibly fast. So it's absolutely transformed the discipline that I work in within 2 years, 5 years. It was kind of the experimental ones a few years ago. So nearly everything that we do now considers the use of machine learning in some way to incorporate it into what we're doing. We're exploring how to use that in flood forecasts. There's lots of different ways you can do it. It is really difficult because rivers are not the same as the atmosphere. The atmosphere is everywhere all at the same time, but rivers kind of flow along a particular line and connected to each other. We're not quite there yet, I think, in being able to produce the best flood forecasts with these techniques, but we'll be there soon. The weather forecasts that are produced by UCMWF are on par and sometimes better than the traditional ones, and they use a fraction of the computational resource that is needed. But it does rely on the big data collection, and it does rely on the big model to start off, the traditional physical model that sucks in all the satellite data and ground measurements and things like that. So it is a hybrid approach at the moment. We are still reliant on the physics and the big computer models, but we can use machine learning already, these AI forecasts already, to take good decisions about our weather.
Are these AI models then, as a result, actually representative of places where it might be more difficult to collect the data? And if that data is lacking, are there techniques to then basically fill in the gaps?
Yeah, particularly places like Africa. There are just so few observations. We have so few measurements of the things that we need. Trying to fill in the gaps is one of the games that we play all the time. We have some good kind of global products called reanalysis, which is kind of a fill in the gaps. It's kind of maps without gaps of weather variables. And also we now have a flood product as well. So that is where we try and use all the satellite data that looks everywhere to try and help fill in those gaps and use the weather model and the flood model to fill in those places. Using machine learning techniques, it's just the same game, but sometimes a little bit faster. You can transfer some information from different places depending on its characteristics. So if you have a very dry catchment that floods every now and again, then you can use those characteristics to fill in the gaps to try and work out what that might look like in certain circumstances. So it's about the speed. I think that machine learning is reliant on the data, actually, and it's actually those new data sources that we're getting, some of those new satellite products that are coming in, those sensors, so we can use everybody's mobile phone, to take temperature measurements or something like that. It's those things that will make the difference to what we can predict. I think then the more that it's going to be a hybrid approach between the traditional way of doing things with these big weather models and individual level doing it on your mobile phone or whatever is going to replace our mobile phones. I'm not sure. I should tell some kind of chips in our arms. So the more that those kind of systems work together, and the more that we can suck individual level sensors into those big systems that are supporting kind of global weather forecasting and flood forecasting, I think that we have to do that. There is no going back from that. I think the involvement of companies as well is really important. So different industrial players are becoming better at weather forecasting and are producing their own weather forecasts, and that is a big change that we haven't seen that before. So if we can use these new techniques to predict something 2 weeks ahead where we could only see it 1 week ahead before, I think that's always the thing that drives me, is getting that information to people early so they can take better decisions.
I've learned how AI is genuinely helping us predict and then better prepare for extreme weather events. During the making of this documentary, the UK experienced 3 heat waves in quick succession, and sadly in Texas, 100 people lost their lives due to flash flooding. This really drills home what an important role tech breakthroughs can play in helping us adapt to our changing climate. But this vital climate data needs to be made publicly available so that policymakers, businesses, and communities can use it to figure out where to build, where to live, and where to evacuate if there is an extreme weather event.